All right, guys. So this is some of the in-class practice. So this is what I make my physical students do when we're in class and we've stopped talking about this particular part of the lecture. So here's what we might be looking at. So use a standard enthalpies of formation table to determine the change in enthalpy for these reactions. We've got NaOH plus HCl goes to NaCl plus H2O. If I look down here, NaCl solid I see as negative 411.0. I see H2O, and it is gas, as negative 241.8. I see NaOH somewhere, better be in this list. NaOH solid is negative 426.7. And HCl gas is listed somewhere. It's gotta be in this list. Where the heck is it? Oh, there it is. I keep looking right past it. 92.3. Okay, now remember, we're looking at products minus reactants with the stoichiometry included. So I don't see any stoichiometry here I need to worry about. So it's going to be the products negative 241.8 plus negative 411.0. And then I'm going to subtract the total of negative 92.3 plus negative 426.7. So products negative 241.8 plus negative 411.0. And then we'll just subtract from that negative 92.3 plus negative 426.7. Negative 241.8 plus negative 411.0. We'll subtract from that negative 29.3 plus negative 426.7. And I get negative 133.8. Now, what I can tell you is, having done this for ages and ages and ages and ages, it is really, really important that you watch your signs with this. Now notice, I wrote down everything with the sign that was attached to it. And then when I wrote it in the next part, it still had the signs. I didn't change any of the signs that were there. We need to do this summation and then subtract this total from it. Okay, so I added together the two negative numbers. I subtracted that negative number from this thing here, and that's how I got that total that you see right there. Watch your signs when you do this math, because it can be very problematic. Okay, that's usually the place I would look first if I made a mistake. So 2CO gas. Well, where's my CO? I see CO2. Am I being ridiculous? And that's entirely possible. I'll come back to that because I can't see anything. So CH4 gas, I see as negative 74.8. O2, of course, is 0. CO2, I see there is negative 3.5. And H2O liquid is negative 295.8. Okay, so I'm going to take my products, and of course it's 2 times negative 295.8 plus the negative 393.5 minus the entire quantity of negative 74.8 plus 2 times 0. And yes, I do actually include that because for me, that makes sure that I've gotten everything that I needed to get. Okay, so 2 times negative 295.8 plus negative 393.5. I'm going to subtract negative 74.8, and of course negative plus 2 times 0. And I get negative 910.3 kilojoules per mole. Okay. Well, cool, that was fun. Over and over. H2S. Negative 20.1. O2 is 0. 2 H2O liquid. H2O, there it is. 285.8. And that SO2. Where is it? SO2, negative 296.1. And so products, we have 2 times the negative 285.8 plus 2 times the negative 296.1 minus the quantity of 2 times the negative 20.1 plus 3 times 0. Okay, happy math. 2 times negative 205.8 plus negative 296.1 times 2 minus the quantity 2 times negative 20.1 plus 3 times 0. And I get negative 1123.6, and that's kilojoules per mole. I am not paying any attention, just so you know, to significant digits at this point. I'm just using whatever they gave me in the event that I needed to deal with that. I would deal with it at the end of doing all of this, but I am not dealing with any of it at this point. Excuse me. Everything that I see here has one decimal place. And since we're doing a lot of addition here, even though we're multiplying by 2, everything should be to the same decimal place. So that's actually not a concern for me here. I should only be reporting one decimal place in my answers. And, excuse me, I see that for everything I have reported. So there is that. There's my commentary on significant figures for this discussion. So I see NO. Where's my NO gas? NO. Oh, there it is. NO gas is 90.4. 90.4. And then we have O2 gas, which is 0. N2 and N2, I think we actually calculated this already. N2 is 33.9. And so we're looking at products. 2 times 33.9 minus the quantity for the reactants. 2 times 90.4 plus 0. So 2 times 33.9 minus 2 times 90.4. That gives you negative 113. Now, CO gas is the one that I couldn't find. I see CO2. And there's O2. Don't see CO. So I don't know how to do this without the CO value. Now, could I go find the CO value somewhere else? Of course I could, but that is not given to me here. So I'm actually going to say that I can't do this without that value and just underline it because I got nothing. So I need to know how much energy it takes to make that CO to be able to figure out what the heat of formation for CO2 is. Okay? Let's see what else we've got. The combustion of methane, CH4, releases 890.4 kilojoules of heat. That is, when 1 mole of methane is burned, 890.4 kilojoules are given off to the surroundings. This means that the products have 890.4 kilojoules less energy stored in the bonds than the reactants. Thus, delta H for the reaction equals negative 890.4 kilojoules. Negative symbol for delta H indicates an exothermic reaction. CH4 plus 2O2 goes to CO2 plus 2H2O. Delta H equals negative 890.4 kilojoules. How much energy is given off when 2 moles of CH4 are burned? Well, I think 2, then I'm going to need to multiply that by 2. Negative 890.4. That gives me negative 1780.8 or 2 CH4, 2 moles CH4. How much energy is released when 22.4 grams of CH4 are burned? 22.4 grams CH4. 1 mole of CH4 is 16.04 grams. Pretty sure that was the number that we came up with. 16.04. Go me. That's per mole of CH4. 1 mole CH4 is negative 890.4 kilojoules. And that gives me 22.4 divided by 16.04 times negative 890.4. That gives me negative 1243.45 kilojoules. And again, no thought has been given to sig figs here. And the number that I started with was 22.4. So I would round this and put it as 1.2 times 10 to the third, fourth, whatever. Put that in scientific notation and report it as 2 sig figs. If you were to attempt to make 45 grams of methane from CO2 and H2O, with O2 also being produced, how much heat would be absorbed during the reaction? Oh, okay, so we're looking at the reverse reaction. So here we have CO2 plus 2H2O. This means CH4 plus 2O2. And my delta H for that equals 88.9. For crying out loud. It's like tripping over my tongue. 890.4 kilojoules. And of course, that's positive because we've turned it around. If you were to attempt to make 45 grams of methane, 45.0 grams CH4, 1 mole CH4, 16.04 grams, and 890.4 kilojoules per 1 mole CH4 produced. So 45 divided 16.04 times 890.4, and that gives me 2498 kilojoules. Woohoo! That's fun. Okay. Questions, comments, problems on what we've done so far? Okay, awesome. Anything else? Ooh, there's more. Use the standard enthalpy and entropy of various substances. Using data from the heat of formation table above, calculate the enthalpy of reaction for 3H2 plus O3 goes to 2H3H2O. Okay, cool. Well, H2 is 0. O3 is 143. So this one is 143. This is 0. And the H2O gas is listed as negative 242. Okay. So 3 times the negative 242 minus the quantity of 143, because I have plus a 3 times a 0. So 3 times negative 242 minus 143 gives me negative 869 kilojoules. And that's per 3 moles. For 3 moles. But I'm just going to leave it as kilojoules. Okay. Using data from the heat of formation table above, because this, again, this is moles, this is kilojoules per mole. This is kilojoules per mole, but I multiplied it by 1 mole. So that should be kilojoules. Using data from the heat of formation table above, calculate the heat of reaction for 2NO gas. I have an NO gas of 90 plus O2 is 0 plus 2NO2, which is 34. So 2 times 34, again, units. 2 moles, 34 kilojoules per mole, minus 2 mole times 90 kilojoules per mole. And I'm not going to include the O2 because we know that ends up being 0. 2 times 34 minus the quantity, 2 times 90 gives me negative 112 kilojoules. Okay, that was awesome. Using data from the heat of formation table above, calculate the heat of reaction for N2O plus NO2 goes to 3NO. Okay, from N2O is 82. NO2 is 34. And NO on its own is 90. So I have 3 mole times the 90 kilojoules per mole minus the quantity 1 mole times 82 kilojoules per mole plus 1 mole times 34 kilojoules per mole. And so I have 3 times 90 minus the quantity 82 plus 34. That gives me 154. Checked my math a couple times, and it's kilojoules, right? So, yay, that was fun. Awesome. More? Oh, using data from a heat of formation table above, calculate the heat of reaction for CaC2 plus 2H2O liquid goes to CaOH2 plus C2H2. Okay. CaC2. CaC2 is negative 63. H2O liquid, negative 286. CaOH2, I see listed as negative 987. And the C2H2 is 227. So products, 227. There's 1 mole of that. Plus a negative 987 minus the quantity of negative 63 plus 2 times negative 286. Of course, it's 2 moles times kilojoules per mole, so my answer is going to be in kilojoules yet again. So 227 plus negative 987. Subtract the entire quantity of negative 63 plus 2 times negative 286. It gives me negative 125. Okay. Many cigarette lighters contain liquid butane, C4H10. Using heat of formation, table above, calculate the quantity of heat produced when 1 gram of gaseous butane is completely combusted in air. Okay, so there are a couple of things I need to do. One, I'm going to convert 1 gram of C4H10 to moles, and we'll need the molecular weight to do that. Cheat sheet. C4H10, 58.12. And I need a balanced equation to be able to work with this. So combustion, C4H10 plus an O2 will give me CO2 plus H2O. That's the definition of combustion. Okay. I need 4 of those so that I have the same number of carbons. I now have H10, so I need 5 waters to deal with the H's. That means I have 5 O's there. 13, so 13 halves. Or I would look at 2 C4H10 plus 13 O2 goes to 8 CO2 plus 10 H2O. Okay, awesome. So now I need to calculate based on that reaction. I'm actually gonna move a couple of things because I can, so why not? Almost got it all. Okay. Yeah, that's 10 grams. So C4H10 I see as negative 126. 3O2. Oh, the O2 is 0. Sorry. CO2. CO2 is negative 394. And then 10 H2O. And now I have to decide, am I going to, let's see. So in air, we typically form H2O as a gas under these conditions. This is a gas. That's a gas. This is actually a liquid, which we knew anyway. But the H2O gas, I see a value for the H2O gas of negative 242. And it really doesn't matter which you decided to do as long as you told me in your equation which one it was. Okay, that's the part that's important. So calculating the value for this, 2 times the negative 126 plus 3 times 0. And then we're going to subtract the quantity of 8 times negative 394 plus 10 times negative 242. Okay. And that gives me, I calculate that to be negative 125 kilojoules per mole. And that's for 2 mole of C4H10. Only this is kilojoules because it's dependent on the stoichiometry for each of those components. So this is what I'm going to get here. So 10 divided by the 58.12 times negative 125 divided by 2. And that gives me negative 10.8 kilojoules. Cool. And that is everything. So that is all of the in-class practice that we would have done. I hope that that covers most of the questions that you had and shows you what we would need to do. Now, do I get lazy in doing these calculations? Yeah, because putting the units on becomes incredibly space consuming. So I don't always do it. But I do usually, and you saw me do it, I do usually check at least one of them to make sure that the units are coming out the way I think they should. Okay. So there is that. I'm going to go ahead and stop here. I will stop this recording, and I will be back with you guys for the laws of thermodynamics. See ya.